Okay, so welcome back. If you remember what we treated in the previous module, we looked into your case-based reasoning, right? So now we will need to investigate the concept of reinforcement learning. As you are well aware, most times when we look into the aspects of machine learning, we actually studied machine learning under some subtypes, right? Or some some subtypes, which we saw ML. In ML, we studied what? Supervised. So let me say some class labels will be provided, right? So L1 to Ln. Then we saw unsupervised. So in this case, there's no class label, so think that some things are scattered here and there. And then another aspect is what we call reinforcement learning, right? This is what we know. And in reinforcement learning, obviously we start seeing what robots and kind of stuff. Now, not that you also have other ones which you call semi-supervised, semi-unsupervised, and or whatnot. But what is reinforcement learning? So before we give a proper definition, let's try to take some real-life examples. So let's start by asking this obvious question. What is reinforcement before we think of learning? Reinforcement is an English word which means to emphasize on something, right? So if I say a word repeatedly over a number of times, you'll be forced to learn that word. See, when I came to India, I was not speaking like most of you. But because I interacted with so many people, especially from Karnataka, I have learned to speak like Canadians, right? Not Canadians. So that's why people always say, bro, you are now speaking like Indians, right? So this is a kind of a similarity between what you hear and what you see people do. So there is an action, right? I'm an agent. I have observed people through my eyes, obviously, by interacting with them. They perform some actions. They nod, okay, TK. I also copied that. Invariably, I have started thinking like them. So what is the reward now? The reward is I have learned to act accordingly. Now, think that you are lost in a jungle. You neither know the language, nor do you know the food. Neither do you know the people. You found something floating on water, and you are damn hungry. You pick that up, and it happened to be some berries, right, which is floating. You never knew that is a berry, but it looks like something that is edible. What will you do first? Is a fruit item or whatever is a fruit? What will you do? You try to taste it, right? You tasted it and it tasted delicious. It's edible. You ate that up. Suddenly you saw a bunch of them floating. What will you do? Nobody will tell you not to pick that up and eat. It's a gift from God, He don't want you to starve, so He has provided that. And then in between, maybe you saw some kind of cans of water that are floating. Remember, you are lost in the jungle. There is a shipwreck and you are drifted ashore, right? So you really need to survive until help arises, until help comes your way. So what you do, you cannot drink that water because it's polluted. So you saw that in a bottle. So and it looks really nice. Yes, in most cases, I wouldn't encourage you to drink, but you are really tired and you saw it's a brand maybe like Pepsi, or it's a brand like, think of which brand? Bisleri, okay? Now, you tried, okay, you don't swallow everything, right? You tested it, fine. Oh, thank God, hopefully your test bud is working, so you eat that up. So this is a kind of an analogy of how reinforcement learning works. So you see, you observe, you try to perform some actions, you receive an immediate reward. So when we normally talk about reinforcement learning, we use that child-parent relationship. So you have maybe a little kid who is maybe in third or fourth standard, and you tell this child, see, I want you to learn Kannada alphabets nicely, and I will give you chocolate. Yeah, I do that most of the time, but So Anna says, see, if you get this seriously, I'm going to give you chocolate. The child said, okay, Anna, I will do. Okay, Chekapa, I will do. So what the child does is, the child reads, nicely and writes, o, and the child is able to write that. So what you do, you give the child what? A reward. Next time when you tell the child, see, it's time for us to study Kannada, nobody will tell the child not to get there, right? Because the child expects a reward. Hence, we said reinforcement learning addresses the question of how autonomous agents that senses and acts in its environment can learn to choose optimal what action to achieve its goal. So the goal is to get a nice marks in a exam for that child. So how will the child learn this? The child knows that if he studies with dad or studies with Chekapa or Dodapa, he is going to get a reward. That reward will translate into what the child performing repeated actions that will yield what a better performance, meaning scoring high grades in the final exam. Now, let's take a robot and then we now think, how can this agent learn this? So whenever you hear of agent now, you think of a robot. So we go by introduction. So consider building a learning robot. So this robot, now when you hear an agent, remember it's a robot. This robot has some sets of sensors and which you use to observe its environment and some sets of actions that it performs to alter its state. Now in this case now, the task can be a control strategy, which can be a policy for choosing what actions to achieve its goal. Now the goal of this agent can be defined as what? A reward function that assigns a numerical value to each distinct action. Sorry, I think squirrels are disturbing us. Okay. So, welcome back. Sorry for the interruption. So, the goal of this agent can be defined as a reward function that assigns a numerical value to each what action that the agent may take from each distinct state. Now, the reward function may be built into this robot, okay, or known to an external teacher, which provides a reward for each action performed by the robot. Now, the task of this robot is to perform sequences of actions, observe its consequences, right, and learn a control policy or strategy. Now, this control policy is one that from an initial point, it has to choose actions that maximizes the reward accumulated over time by the agent. Now, let's put all these things together. You know the game of Go? Yes? So when we talk of reinforcement learning, what comes to our mind is game playing. Again, autonomous driving vehicles. And then we talk of robots. So let's take game playing. The game of Go is considered to be the hardest board game ever. And they say there are about how many million strategies as there are, that there are so many million strategies as there are the number of galaxies in our entire universe. And there is an AI called AlphaGo, developed by, obviously, Google, its parent company, Alphabet, that defeated the 12-time Go master. He's actually a South Korean, I can't get his name, I think something Sidol. Right? And the objective function was to see who wins. Whoever wins will receive a reward of, I think it was $1 million, right? Now, they played 5 games in a series, in a stretch, in which AlphaGo defeated the Go Grandmaster by 4-1. So he was able to only win in one of the game, but AlphaGo gave him a kind of, it was like 80-20 variation. Now, because of this, Google now said, because of this, the Grandmaster himself said he is resigning from any competitive game, that computers are invincible, meaning you cannot actually defeat the AI system. But what was the strategy that the AI system employed? Google trained this AlphaGo based on some strategies which he has learned and made this robot to play this game over and over again. I heard he played it 100,000 times. I think more than 100,000 times. It learned all the strategies. Now you can imagine if a human has to learn those strategies, it might take them a lifetime, still they will not be able to master it. Now, on the day of reckoning, this intelligent robot beat this human competitor hands down. Now, what happened was, when doing the reinforcement, it has made mistakes, right? So it learns the optimal solution to that, updates its state, and moves to the next state, right? thereby optimizing the approaches it followed. Hence, when you think of an example of what a mobile robot, which have sensors and cameras and sonars and actions, such as what? Move forward, it moves forward, turn, it will turn, yes, jump, it can jump, no doubt. Then this robot might, as it continues to roam, it will also have the goal, which is to dock its battery in the charger whenever its battery level is low. You see it in your phone, right? Most times if the battery goes beyond the threshold, it will tell you to turn on what? Battery saver. Or it tells you the battery is low, please connect charger. Alright? So in this case now, the robot should do this autonomously without human intervention. So what the robot will do is, whenever the battery gets beyond a particular threshold, it should dock itself to the charger. And when it does this successfully, it receives a reward. So the goal of docking this battery charger can be captured by assigning some positive reward. Say if it docks properly, it gets a reward of 100 points. If it refuses to dock or it forgets to dock, it gets -0. If it docks in between but it was not proper, it might, sorry, not -0, it will get -100. If it refuses to dock when it was supposed to dock, okay, it gets -0. Then if it didn't, if docks, docking means it goes to charge it to recharge itself. If it goes and it didn't position its battery properly, then it gets maybe a 0 score. Now you see that it is a state action transition, right? So the state is, the battery is low. Then what is the action? Go and recharge, right? Now that is also possible with even autonomous cars like Tesla, which I heard is coming to Karnataka. And that's a good news, right? So now you see there is a state action transition that immediately results in connection to what? A charger, right? And a reward of 0 to every state action transition. Now that means, see, if it moves from that dead state to a fully, an empty state where the battery has drained to a fully connected state, we update its what? Reward. Now, reinforcement learning problem here, we can actually view it this way, okay? That the reinforcement learning problem can be such that an agent interacting with its environment, the agent exists in that environment described by some possible sample space. So if you put here now, we say, let's look at RL problem. So reinforcement learning problem. So that means that there is an agent problem. So there exists an agent, receives some reward, a reward. So what is the reward? R, or some set of reward R. Yes? That indicates is what? Value of this state action transition. So moving from one state to another, it receives a reward. So moving from one state to another is called state action transition. State action change. That's what we mean by transition. State action transition. And when this happens, what will be the task? The task will be to learn a control policy that maximizes the expected sum of these rewards. So when you play a game of PUBG, okay, what you do is you want to defeat all the opponents, right? Getting to the top. So you want to maximize this policy such that you become the higher ranker. So what do? So you now look for the control strategy. Maybe eliminate the opponents even at first sight or something. And with future reward, you try to exponentially maximize on your delay strategy, right? So the agent task here is to learn a control policy that maximizes the expected sum of this reward. So let there be a control strategy, a control policy, or we call it what? Control policy. So we give it a name, which includes your what? State action transition. So that control policy will be a function. Control policy will be a function which we call pi, such that, right, it implements what? The state action transition. So this is the policy. Yes? And with this, we will look into how this agent can be represented. So let's look at it this. With this policy, it can be represented as, as what now? So I'm going to use this side, okay? So we have an agent. In this case, you can think of a robot that needs to interact with the environment, right? So for it to interact with its environment, it has to move. There will be some actions which has to be performed. Okay? And when it interacts with this environment, it receives a reward. Now, it receives a reward. Now, this is the reward, don't forget. It receives a reward R. And in most cases, when it receives this reward, either it will remain in the previous state or it moves to the next state. So, let's say this is the state transition. So, based on this reward, either it can remain there or it moves to a different state. Right? So, with this, let's try to kind of model this, that it will look like your what? Your automata theory. Now, the principle of automata says, in most cases, is like, if an agent interacts with an environment, receives a reward, either it remains there or it moves to the next state, right? So if you look at it this way, let's say that the agent starts with state 0, which is your initial state, right? So in this state 0, it needs to move to state 1, right? So what happens is, it performs an action, A0, receives a reward, and moves to state 1. In state 1, what it does is, now think of it as level. I'm inside with level 0. Now I've gone to level 1. I need to move up the ladder, right, to level 2 or 3. So what happens is, in level 1, I again perform similar action, A1, receive similar reward, I move to state S2. Now, how many states are possible here? So if I do one more, maybe from here, state S2, I perform an action A2, receive a reward R2, and move to state S3. Now I can do this repeatedly until I get to state Sn. Right? So what is the goal? The goal is to learn to choose the action that maximizes what? The objective function. So beta is a constant value. So when it moves to this, now this is an exponential problem, such that R2, right? If it transitions to R2 with what now? This beta, this is the reward it receives. But this function becomes what? Exponentially incremented. So I have what? Beta 2. Now it moves to again, it receives a reward when it goes into R3. And then I have what? Beta cubed. And this continues until it gets to what? Rn beta n. So we have receives a reward, of Rn, and then this becomes beta what? N. Right? But we know that this value, beta, okay, must lie in the range of what? So we write it as must lie in the range of 0 and 1. So how do we write it? We now say where beta lies between 0 and 1. So what does this tell you? That beta can actually be 0, but it must be less than 1. And that makes sense because in most cases, we don't actually go beyond 100%. So you can get 99% because up till now, we have not achieved what we call artificial super intelligence or even artificial general intelligence, whereby the autonomous agent will be able to behave and mimic human behavior to that professional level. That's why we see that beta can be 0, hence we use this less than or equal to 0, right? And then, but it must be less than 1. So there are reinforcement learning problem characteristics, which we're going to discuss briefly. So what's the first problem characteristics? Is we have what we call what? Delayed what? Delayed what? Reward, right? So I'll take the I'll take them points-wise, delayed reward. The second problem is what we call acceleration. partially observable states and the fourth one is lifelong learning. All right. So, if we look at this point, do you need explanation for this? So we go through them quickly. When we talk of delayed reward, what we are actually saying is that the task of the agent to learn a target function, that's pi, right, that maps from one current state to an optimal action, right, and that in reinforcement learning, this agent faces the problem of what we call what? Temporal. I will repeat again. That whenever an agent wants to learn a target policy, like pi, that maps from what? States to what? Action, state action transition, that this agent always faces the problem of what we call what? Temporal credit assignment, which says that it's very difficult in determining which of the actions in each sequence are to be credited with producing the eventual reward, right? So let's say it took so many passes at a particular time, right? Now, which of them do we actually credit with that reward that led to that optimal solution? So this is the concept of what delayed reward. So simply put, that whenever this agent wants to learn a control policy, such as we have a function that implements the state action transition, that this agent always faces the problem of temporal assignment, temporal credit assignment, whereby it is difficult in determining which of the actions in each sequence are to be credited with producing the eventual result. Now, when this agent is doing this, it influences the distribution of training what? Examples by action sequence it chooses. It will raise the question of which what? Of which experimentation strategy produces the most efficient learning. Say, example, when we want to optimize the performance of maybe say a neural network, we might do what we call what? Parameter tuning. We might actually adjust the weights. I mean, obviously we update the weights, but we might actually try to fine-tune that by increasing the number of epochs or something. And most times we now say, okay, this was actually what translated into a higher efficiency. But in this case, in exploration, especially in autonomous agents, the question arises in which we want to know which experimental strategy produces the most effective learning. Now, there is this, what we call what? A trade-off in choosing whether what? To favor exploration of unknown state actions or to favor the exploration of known, which is has already learned by producing a greater reward. So this is the problem of exploration. And we talk of what we call partially observable states. So when you remember when the agent moves around, it uses its sensors to perceive the entire state of the environment in a kind of a particular time interval. But in many practical scenarios, okay, the sensors provide only partial information. That's what we talk of, like in most cases, if an agent wants to, maybe like a robot that is trained to move only during the day, right? Definitely the cameras cannot capture 360 degrees view. Okay, even if it's able to capture, how about when in various various illumination, in which maybe at times you get partially occluded objects and some stuff. So you see that these agents will not give you an entire environmental setup. Most times, practically speaking, it provides only what? Partial information. Now, in such a case, this agent needs to consider its previous observation together with its current sensor data, right? When choosing the actions. And the best policy may be one that it chooses specifically to improve the observability of the what? Environment. And that makes sense because in a case where it encounters a novel challenge, what it has to do is to refer to what? The previous states, right? And try to update that and then see if you can actually improvise on that. Now, with that, we get to lifelong learning. And the key here is that the robot is required to learn several related tasks within the same environment using the sensors, right? So many tasks has to be learned, and these tasks can never be learned in a computational time because in various scenarios, you get what? Heterogeneous forms of data, you get noisy environment, you get all kinds of environment. So the learning task is MDP, which is Markov decision process. if you look at it this way, this says that there is an agent which control policy is to transition from state to action, in which it looks at these states at a present timestamp, performs its actions, okay, at this particular timestamp, and updates its state, right? So that the new transition will look like this at a particular timestamp to this action at a particular timestamp, right? Now, the environment responds by giving this agent a reward, right? And that looks like this now. There is a state action transition which is based on reward, right? So what we'll have is the reward at this timestamp becomes what? Reward of this state at this timestamp and the action at this timestamp. So this is what we now have, right? This is the updated notation. Okay? So when this holds true and it will produce the succeeding state. So what would the succeeding state look like? So it has to transition now from this present state, which is R, to the next state, T plus 1, right? Into what? Now what happens here? For it to transition to the next state, this has to look at what? The partial, it has to compute the partial derivative of the state action transition. So because it has now updated this state, right, to the next state, so we now compute the partial derivative of this state to action transition, and not on the previous state actions. And that made sense because if you see here, this is the reward at this time step or timestamp, which is what represented as a function of what the state action transition at that particular timestamp. And if it wants to go to the next state now, it has to update this by computing the partial derivative of this. And we know that this is only dependent on the current state and not on the previous state action transition. Now, the task of this agent is to learn the policy, right? This was the policy which we know. This was the policy. How shall we specify this policy? And that, that we would like the agent to learn. How do we specify it? One approach is to what? Require the policy that produces the greatest cumulative reward for this robot over the period of time. And to state this requirement more precisely, we define the cumulative reward. So we define a cumulative value. Solution is what? Define a cumulative value. Reward at this state plus reward at this state plus 1, right? That was what we saw, right? Good. Plus reward at this state plus 2, okay? But if you remember, this I'm trying to give you a different notation, okay? Anyway, now, and then it continues, right? It continues till reward at the state of what? N, right? Plus, this is the reward as the state of what? N. But if you remember, we actually multiply this by a constant which we call beta. So this is beta raised to power 1, no problem. This is beta raised to power 2, right? So, and then we continue to beta raised to power n. Out. Going from this reward at that present state, including the next state and or whatnot. So, and that is it. And we notice definitely again that this will hold true provided that what? This beta lies between 0 and 1. Right? Fine. Now, we say that if we set this beta to be 0, that means that only the immediate reward is considered, which is very important. And if we set it closer to 1, future reward is considered. Now, and this quantity, which we call cumulative value, is called the discounted cumulative reward, okay? Which is achieved by that policy from its initial state. So, with this, we look into the next concepts. The finite horizon reward looks like this, but it's a little different. So can I wipe the board now? So if I call this equation 1, now next I'm going to look into the finite horizon reward. Next is your finite horizon reward, in which you have what? Summation of what? I from what? 0 to what? Horizon. I is going from 0 to what? H of what now? the reward at what? That's t plus I, right? At that timestamp plus I. So this holds true. And now, if you consider this now, you know that this happens over h number of steps. That is over the horizon number of steps. And another one is what you call what? Average reward. Furthermore, average reward equals average. So we have finite horizon. We have seen the cumulative value, finite horizon, and the average reward will be equal to what? Limit as this h tends to infinity into what? Into what? 1 upon over some set of steps, right? Summation, and we repeat this. Summation of what? As I goes from 0 to what? H r t plus I. So we have seen some three formulae now. Some three formulas. 1, 2, and 3. Fine. And if you combine the average reward that maximizes this cumulative value, and this policy is called the optimal policy. Finally, optimal policy yields, this yields the optimal policy. This yields the optimal policy. Such that the argmax of what now? The cumulative value of what? Pi. So which makes sense now? Cumulative value of pi, okay? And this happens in what? In the state, right? So cumulative value of pi in this state for all what? This will hold true for all what? States, right? So this holds true for all states. And with this, we look at a classical example. So, for example, let's consider a grid. Let's consider a grid that consists of what? 2 cross 3 matrix. So in which we have 2 rows and 3 columns. So let's fill it this way. Okay? I think I'll have to highlight this, right? So, and here we have what we call the optimal state, or we call it the goal state. Not gold, okay? I'm talking of goal, G-O-L. So the goal of this is to get to this, okay? Listen. So that if it gets to goal state, right? If it gets to goal state, it will do what? It will remain in this state. Okay? It will remain in this state. Now, there will be what we call state action transitions, right? There is what? Movement from this state to that state, and it gets a reward, okay? Okay? Now, again, there is movement from this state to this state. Again, this state to that state. Moves back and forth. Again, this state to that state. Again, goes here and doesn't come out. Okay? So here also, you can move in both ways, right? This state to that state. But again, it goes here, it doesn't come out. Now, when it goes into this goal state, it receives a reward of 100. When it goes into this state, it receives a reward of 100. So we can actually represent this as the reward of what? State action transition, right? Which it receives, we say it receives what? Immediate reward. Okay? It receives immediate reward, which is what? Some sets of some numeric value. So state some numeric value. Now, since it goes back and forth, so we can give this name. So this is G. So we can say this is state A, B, C, D, and E. Now that should have been F, but anyway, I called it G. So when it moves from state back and forth, A and B, so it gets reward of 0 because it goes out and comes in. We say this fellow is playing. Goes out and comes in, goes out and comes in, goes out, goes up and come back, goes right, and then comes left. So then the reward here is they are all 0. Only when it reaches the goal state. And when it reaches the goal state, it remains there. So this is what we have in this case, right? Now, in real life, this is not what we always get. Now you see that these are kind of what possible locations. So the immediate reward in this environment is defined to be 0 for all state action transition, except the one leading to what? The labile state. And that is what we represented there, right? Now, the state G is the goal state, and the agent receives reward by entering this state. Hence, you saw that, right? Now, once the state, the actions, and the immediate rewards are defined, then we choose a value for the discount factor. So, in these cases of using beta, we can use what? Gamma, right? So, call it gamma to determine the optimum policy for its value, okay? Such that the optimal policy here, we choose this value. Remember when I gave you beta, okay? So, let's choose this value, the same beta now, the beta value. Remember, we need to get into this state, which is the optimal state, right? For me to get into this optimal state, that is the goal, right? Optimal state is my goal state, right? So, G, I need to choose I need to choose some constant. So, this constant, we call it what? In this case, beta. You can call it gamma. It doesn't matter. Which is what? 0.9. Remember, the optimal policy is the one that maximizes this objective function. So, for me to get there now, let's consider some scenario in which the initial state, so we have initial state, to intermediate state, and finally to your what? Goal state. So the initial state, we start with, again, the grid consisting of 2 cross 3. Intermediate state obviously will be the same, consisting of 2 cross 3. And your final goal state will be the same, consisting of what? 2 cross 3. Fine. Now, the goal state will not change. The goal state will be the same. When it enters, it remains. Goal state enters, remains. Goal state enters, remains. Now, I need to know which policy that will maximize this. So, let's start with assigning some random values. Now, please listen. If I start by assigning 90, so what I'm doing is 0.9 of 90 is what? So, 1/10 of 90 is 9. So, when I subtract 9, if it goes back, it loses this, right? Think of this. Moves forward, it gains 9. Goes backward, it has to lose 9, right? So, if it loses 9, this value becomes 81, right? So, if I assign 81 here, please listen. Going this way, so now we do something here. When it moves from this state to this state, remember state C to A, then remember 81, okay, it comes here. So, moves here, it gets 81. Moves out, it gets what? Subtract 9 from 81, that is 72, okay? Now, you think of this way. So, moves here, it is 81 because it gains 9, right? It gains 9. It has come down. Gains 9, it is 81. Moves back, it is 72. Now, it is 81, right? So, if it gains 9, it becomes what? 90. Sorry, 90, I'm writing 80. Moves down, it is what again? 81, right? Okay? Now, with 81, if it goes to this state, it becomes what? 90. With 81, if it goes to this state, it becomes 90. Goes back what? It becomes what? 81. Now, with 90, if it goes up, what will it be? With 90, if it goes up, what will it be? It becomes 100, right? So, 100. Now, in this case, it doesn't move down, right? And this also moves here, gets 100, right? So, this is what we'll have. Okay, I hope you can see the board. I tried to squiggle the whole thing inside there. Now, with this, I now need to consider what? The optimal value. So, here I call now the intermediate, I call the arg max. So, when I call the arg max, the state transitions will be there. Remember, we saw something like this: up, down, right, left, up, down, something like that. Right, left, up, down, okay? Then, sorry, no up, down, please. Up and right, okay? So, what we know here is, in this case now, we take what? The maximum, right? So, if we take the maximum, what we notice here is, in this grid, if we call max on this, so what do you think will be here? 90 will be here. Agreed. We call max on this, what do you think will be here? 81, because you see 81 is in this. Okay, I'll repeat again. 72, 81 is in this. See if I do this, okay? So I have 81 here. I call max function on this. Remember, it moved this and this. So I'm going to get 100. Now I call max on this. What do you think I will get? 90. Now when I call max on this grid, what do you think I will get? I'll get 100. Now, in these two, remember there is no going out, right? So the goal state, I can actually update the value to be 0. But let me leave the value, I will not update it here. Now if you look here, which one gave me the optimal? The maximum is this direction, that direction, that direction, that direction, right? Hence, what we see in the final state is which direction? Can you guess? So there is a direction here, this way, up, and this way, right? Fine. And that is what we get when we call this policy. And with this, this becomes my goal state, which is my what? V star or whatever, okay? Yes? So, the discounted reward for this goal state becomes, now we now say, such that the discounted, therefore, discounted reward will be equal to what? Will be equal to what? Can we write something now? Yes. 0 plus what? This alpha, which you have chosen, right? Alpha into 100 plus alpha squared into what now? Is it going to be 100 squared? Is it going to be 100 squared? In that case, you got what? 0, right? So if you multiply this by 0, this actually disappears. But let's put it as notation. Actually, this is what we have. Because if you multiply this by 0 and even go to cube multiply by 0, all these two will disappear. So this is actually what we have. Okay? Fine. And with this, you now see if you compute this value now, what you're going to get is, you take this, right? Because this will disappear. You take this, even if 0 also doesn't make sense. So what is alpha now? Alpha was determined at what? 0.9. So if you call this function and say 0.9 of 100, which gives us what? 90. So the optimum value here is 90. So with this, we wrap up with on the model of what? On this section on what? Reinforcement learning. Don't forget how we started. So let's try to recollect what we did. So we started by first of all looking at reinforcement learning by taking a kind of what? A real life example that this is modeled after the behavior of human beings, right? So where we learn by what? Reinforcing whatever we have learned. That if I keep speaking, talking to Canada people, I will learn to say go tila like you, go taitu, and go to, right? So after that, we looked into what? A classical example of what? Mobile robot navigation. And we looked at how a reinforcement learning problem works by maximizing the policy or the objective function. And there we looked at the block diagram where we saw the agent interacting with the environment through some specific actions in which it's what gets a reward by moving to the next state or remaining in that previous state. And we saw the problems associated with what? Reinforcement learning, which includes delayed reward exploration, partially observable states, and lifelong learning. And we actually saw some instances in which we actually tried to define some terms, which we saw as optimal value, and your finite reward, finite horizon reward, and your average reward. And with that, we now got to the example in which we want to maximize the objective function by considering the state action transition. And we took a classical example, and that was what led us to this. And this is your optimal policy. And the optimal policy, which is your discounted reward, became this. And with this, we will wrap up this class, and we will continue with Q-learning in the next class.